So we are very delighted to welcome all the teachers and students from SNGK College, Pothencourt, to this two-day workshop on drafting of foundation courses. As you know, the state of Kerala is implementing a new curriculum framework for the undergraduate stream, not for the B.Ed stream, for the regular courses in affiliated colleges. And we are making a lot of preparations in this regard and consultations with experts. And we are also trying to create some content or model for foundation courses which will form an important component of the new 4-year undergraduate curriculum. For that purpose, we have formed a committee, and the committee is headed by none other than Dr. Mohanan. He is a linguist, he is internationally acclaimed teacher. He has vast experience in different parts of the world. He was in the United States of America, he was in the Singapore University, he was also a leading teacher at the ISER Pune, and he is a native of Thrissur. He is well accomplished in his profession, and he is very happy to interact with students than with teachers. So that's why we have invited a select group of students to this program. So on behalf of Kerala State Higher Education Council, I welcome all the students and teachers from the Pothencourt B.Ed College and also Dr. Mohanan to the class. So he will be taking the class, and we have made some arrangement for video recording of the entire session, which will be beneficial for other students and other institutions in the coming days. So thank you.
So I assume that all of you are B.Ed students. It's a 2-year B.Ed program or the 4-year program?
2-year.
2-year, okay. I looked at the syllabus of the 2-year B.Ed program, and I found this course called Perspectives on Knowledge and Curriculum. Do you have that course in your syllabus? Yes or no? Does the B.Ed program have a component called Perspectives? No. Okay. Do you have a course called Knowledge and Curriculum?
Yes.
You have. Okay. So I was looking at that. Have all of you taken that course, Knowledge and Curriculum? Or yes? Yes. Say yes or no.
Knowledge regarding curriculum is a part of their syllabus. Then
Is there a course called Knowledge and Curriculum? No. The curriculum is part of the syllabus.
yeah, curriculum construction, all those things are part of their syllabus.
Okay. And knowledge is also part of it.
Yeah, knowledge is
Okay.
also.
So even if you haven't taken that particular course, I can find out how much you know about. Can I have a copy of the PDF? Yeah, you could do that, but could I also have a copy of the PDF? Yeah. Okay. So this is a copy of the PowerPoint slides that could be projected there, but you can scribble on it and find out. Okay, so I'm going to focus my attention on these two words. And begin by saying something about them. What do you think knowledge is? What is knowledge? When you go to school, you acquire knowledge, right? So what is it that you acquire? Obviously, you don't acquire idlis, you don't acquire chairs, you don't acquire clothes, you acquire knowledge. What is it that education gives you? What is knowledge? Okay, if you have, I'm not sure if you are used to interactions. I'm not here to judge you. I'm just trying to find out what your expectations are. Okay. So talk to the people sitting next to you. Spend about 1 minute to find out what your ideas are about knowledge and share them with me. There is no correct answer or wrong answer. All right. Will someone share with me what your ideas are? Yeah. You're going to say something.
It's that new information we gather
Information that you gather from
all over.
all
Yeah.
over. Okay. New information we gather. Okay, so tell me what you had for breakfast this morning.
I had steam cake.
You had
Steam cake?
same here. Sorry.
Steam cake.
Same. Okay, steamed cake. Okay. All right. All of you heard that?
Yes.
What did she have for breakfast this morning? Steamed cake. So is that knowledge, information? Is there a difference between that information that you shared with everybody and the kind of stuff that you get from schools, colleges, universities? Did you learn anything about what she had for breakfast in your degree course? No. So that's not the kind of information that you get, right, from your school and college. So what's the difference between this kind of information that you just now gathered and what you get from schools and colleges? Okay, talk. 1 minute. Alright, so what's the difference? What's the kind of knowledge that you get from schools and colleges? Can somebody share? The second question has to be answered by somebody who wears light green. I don't know what the color is. Yeah. Are you a student or are you?
Yeah, I'm
Okay, then you get volunteered. You don't have to stand.
The knowledge we gather from schools and all is mainly a pattern.
Is
It's structure. There is a structure for which.
there is a structure, okay? Is there any other difference? Yeah, that's good. Any other difference that you can think of? Somebody else? So one difference is that this is just one piece of information, whereas the other is the knowledge that you get from schools and colleges is structured information. Any other difference that you can think of? So they're connected to other things. Somebody who wears green, you get volunteer. This is best to that you volunteer, you know. Otherwise, I become on the basis of color or the length of hair and so on. Yeah.
For our future, for helping for problem solving.
Okay, so it helps you to do problem solving. many such differences. I'm not going to go into the details of what that is, but people would say that this, what you get in schools and colleges is academic knowledge, okay, which is different from other kinds of knowledge, personal experiences, what you had for breakfast, and who the name of your grandfather, grandmother, sister's daughter, and so on. These are not things that you learn from schools and colleges. This is your personal knowledge. Okay. Now, let me take a look at okay, that one. Okay. Look at the slides, or you can look at the slide here. Before you went to school and college, whatever, your primary school, what was your belief about the earth and the sun? Did you believe that the earth went round the sun, or the sun went round the earth? What was your belief? The earth went round, sorry, the earth went round the sun? The sun went round the earth. This is natural, this is your experience, because you see, when you stand here or anywhere, you don't feel the earth moving. Your experiential knowledge is that the earth is completely stationary. And of course, you see the difference in positions of the sun, so you say, okay, the sun goes from east to west. Do you believe that now? No. Why not? Your textbook says something opposed to what your experience tells you. Why should you accept the textbook and reject your experience? What's the reason? Is there a reason for it? Come on. As I said, there is no right answer, wrong answer. I just want to get to know you, that's all.
Text is a part of
Yeah.
the curriculum. It's valid information.
Valid information. How do you decide that the earth goes round the sun is valid? Why not your experience? Experientially validated information.
Describe the information
Yes.
more accurate.
How do you know it is more accurate? It's essentially what your school textbooks tell you, right? So textbooks are a form of authority, and it's a better authority than experience. And therefore, that's your argument. Therefore, the earth going around the sun is what you believe now. You reject your experience. Okay, I would like to think about for a little while. Keep that in mind. Is it a good idea to reject your experience in terms of what the authority tells you? Question number one. Question number two. How did the authority decide that the earth goes around the sun? Because after all, before 15th century, 16th century, all authorities agreed that the sun goes around the earth, right? So this is a different authority. On what basis do you accept the new authority and reject the old authority? Because whatever is latest? Yeah?
Evidence-based.
It's because it is based on evidence. Okay, now let me change my question and say, what evidence do you have to believe that the earth goes around the sun? Do you have any evidence? So if you're all going to be educationists, educators, teachers, something, you're going to teach after you get your degree, right? And a student of yours asks you this question, why should I believe what you're saying? What is your answer? And some smart student is going to ask that question. If I were a 15-year-old and I was in your class, I'm definitely going to ask that question. I did, and I was thrown out of my classes. And they said, shut up and learn what we're telling you. Okay, of course you can do the same thing. But surely you don't really want to do that, right? You want to give a good answer. What would be your answer? What is the evidence?
Technology has advanced.
Technology?
Advanced technology.
Advanced technology. Okay, so you're essentially saying, now we have advanced technology and you can go using a rocket somewhere and see whether the earth is going around the sun or not, right? Is that your idea? Intuition. You have the intuition that the earth is moving? That is the opposite case, right? Our intuition in terms of experience, I don't experience the earth moving. Yeah?
So actually we have no direct experience to prove all those things,
Uh-huh.
but we are going through certain books or other sources, we can identify that all these things are right.
Okay, so
Compared to
tell
our
me,
experience.
what evidence do
Yeah.
textbooks give you to show that the earth goes around the sun?
Yeah.
What's the evidence? Scientifically proved, you're saying some scientists, authority scientists have decided that is so, but what do you know about the evidence, is my question. Of course, you can tell the students, some authority has decided that is so, therefore it is true, but you don't want to appeal to authority, right? Because authorities also change. Okay, I don't want to extend this, because if I really ask you that question and ask you for evidence and argumentation, it'll take at least 3-4 hours just on that question. I just want to impress upon you, this is an important question that you must consider if you want to be good teachers. When a student asks you, why should I believe you? And you say, textbook says so, and the student says, why should I believe textbooks? And you say, oh, textbooks repeat what the scientists have said, and the student might ask, why should I believe the scientists? This is an important question for scientific inquiry. A good scientist will never say, because the scientists say so. They have to give you the evidence. And teachers will also do the same. That means you have to figure out what the evidence is. Okay? If you ask me that question, I'll give you the evidence and arguments. I am not going to do that because I want you to be uncomfortable about not knowing the reasons for why you believe this. Out of that discomfort, if you take steps to find out, you will have some knowledge of the evidence and arguments. Okay? Another question. Your experience tells you, if you look at the night sky, that the moon is bigger than the stars. I'm pretty sure that you did believe that when you were children, right? This is a common experience. You look at the moon and say, of course, much bigger than the stars. And I'm pretty sure you don't believe it now. What's the reason? Distance. How do you know that the stars are farther away than the moon? It may very well be that the moon and the stars are all on this thing called sky. Sky is a dome, and the moon and the stars are just pasted on that globe. And of course, they're the same distance from the Earth. How do you know that? What evidence? Okay, I will not prolong this agony, but I still want to point out that you don't have an answer. Other than that is what the textbook says. That is not a good answer. Especially if you are going to become teachers or educationists or textbook writers, whatever. Let me ask. Number 4, worms and humans are not animals. Do you think so? Question number 4. Worms and... this is easier, thank you. Worms and humans are not animals. Are worms animals? Yes or no? Worms are not animals. Are humans animals? Yes? Worms are not. Okay? Interesting answer, I wasn't expecting that. Incidentally, if you consult a biology textbook, what will it tell you? Are humans animals? Yes. Worms animals? Okay. Anybody who has done biology here? Anybody who has done biology? No? You have. Okay. What do biology textbooks tell you? There was a guy called Carl Linnaeus. How how did he classify our worms? As animals or non-animals? Okay, I can see that you're getting nervous. Don't look at my face and whatever and get worried. I will not bite you, definitely. Don't worry. Okay. So let me just say this. You should look at the internet, some biology textbook or Wikipedia entry, whatever it is, and find out what the biologists think. Okay? Your early experience was that worms are not animals. And I'm pretty sure that any biology textbook will tell you worms are animals. My question is the same. Why should you believe the biology textbook? Okay? What are the reasons for classifying worms as animals? Okay. Now, in all these questions, I'm not going to discuss all of them. I'm pretty sure that you had the idea plants are not living things when you were 5 years old. Very few 5-year-old children believe that plants are living, and they're surprised to see that plants are, to be told that plants are living things. The question that I'm repeatedly asking you is about evidence, reasons, arguments, etc. And the essential difference between academic knowledge and other systems of knowledge is that academic knowledge requires you to understand the reasons for belief. You can't say some authority told you so. And that is what you have to have your students acquire the ability for. To evaluate the evidence, evaluate the arguments, prove whatever it is, reasons, and say, I believe this for such and such reasons. Any questions till then? Any questions? Just ask. It's okay. If I don't get questions from you, when I go back to Pune, I'm going to tell my wife I had a session with students who did not interact with me at all. And she's going to become very sad. So to prevent her sadness, you have to be a little more active. Okay. And I realize that my appearance is somewhat forbidding, grey hair, grey beard, big. And that is not conducive to conversation. But please try.
Sir,
If you don't try, then my wife is going to be very sad. Yeah?
Sir, I think in a school curriculum, it is not possible to give evidence for each and every aspect.
I agree. It is not possible to give evidence and arguments for every sentence. But something like the Earth going around the Sun is one of the major pieces of the worldview today. Something like humans and animals, humans and worms, both being animals, is part of our worldview. These are some of the important statements. The water being a compound and not an element is a very important part of substance theory. Air not being an element. Why should we believe all such important things? Right? Evolutionary theory is an important piece of knowledge. So these are things that we should give evidence for, not everything in detail. And the reason for doing that is because then the students would begin to realize that knowledge, academic knowledge, is based on evidence and arguments. It is not simply somebody's authority. And they will then learn to question the kinds of things that they would like to question and leave the other things aside. You cannot really ask for evidence for everything. It's impossible. That will take you about 30,545 years and several months to do that. And you won't be alive for that long. Are you sure that you will not be alive for that long? You are sure? How do you know that you are not immortal? How do you know that you are not immortal? That is not an easy question to answer. Okay. If I had a semester with you, this is one of the questions I'm going to ask you. And you'll have to figure out a good answer. Okay, so let's go through a few more tasks. Now that you've had some experience of these interactions, the purpose of this session is what is there on the slide. To give you a taste of what we mean by academic intelligence. academic intelligence is the kind of intelligence that you develop by engaging in academic inquiry, the kinds of questions that we raised earlier. You develop a certain kind of intelligence. And this is the same as saying how to think like a mathematician, how to think like a scientist, meaning physical scientist, biological scientist, human scientist, how to think like a philosopher, how to think like a historian, and so on. These are all academics. They all have certain common characteristics, but there are also certain differences among them. A mathematician doesn't think like a physicist. A physicist does not think like a sociologist or an economist. There are certain different flavors, but there are also certain common cores. So how do you help students develop those abilities? My purpose is to give you a taste of that. That is also called, have you heard about NEP 2020? You have? Yes or no?
Yes.
National Education Policy 2020. Okay. How many of you have read it? Okay. Don't read the whole stuff. It's way too long. But download that document and do a search for higher order cognition. That word there. Okay? Now, NEP 2020 recommends that all students acquire higher order cognition. What does that mean? It means roughly the same as what I meant by academic intelligence. It is also roughly what the Constitution says about the scientific temper. If you generalize from the scientific temper to the academic temper, that's what we're talking about. So there are different words for describing certain kinds of mental abilities that you can acquire by engaging with academic knowledge. So my purpose in this session is to give you a flavor, a taste of what that is like, so that you can decide for yourselves whether you want to acquire more of that type of intelligence. Yeah? Now, of course, you're going to ask me, but can you acquire intelligence? Is intelligence what you're born with? No, intelligence is like your capacity to do things with your body. Intelligence is something that you can acquire through appropriate exercise and appropriate nutrition. So if you try really hard, 10 years from now, you'll be much more intelligent than you are now. But if you do not exercise your mind, your intelligence will be much weaker. That's the risk that you have to take. Okay. So if you value it, if you value intelligence and if you value academic intelligence in particular, it may be a good idea to acquire these abilities. And this is what the National Education Policy, one of the things that National Education Policy recommends. And I think it's a very good suggestion. There might be things in the policy that I don't agree with. That doesn't matter. This is one thing I do agree, and I will take steps to get there. I don't think there is any policy paper that doesn't talk about critical thinking. Everybody talks about critical thinking, and my experience has been nobody knows what the heck it is. So it's a good idea to know what it is so that you can nurture critical thinking among your students. Critical thinking is not criticizing other people, it's something else. So ask yourself the question, if you're given a mathematical proof, can you subject that to critical thinking? What do you think? You're given a proof of a theorem that Euclid gave long ago. Can you subject that proof to critical thinking? If you have some experience of that, then you understand what critical thinking is. If you think that critical thinking is useful only in politics and politics and history and literature, then you haven't fully understood what critical thinking is. So, what I'm going to do is for the rest of the remaining time, I'm going to take you through a few tasks that illustrate critical thinking. All right, so please ask questions. Please raise comments. Just convince me that the humans who are sitting here are alive. Not alive in the sense you can move your hands and legs. I can see that. But that your mind is active. You have to give me evidence for that by asking questions or answering questions. Okay. So all of you have seen this famous candle experiment. What that does is you have a candle, and you keep that candle in a tray of water. Okay. Water. Seen this, right? There are YouTube videos and textbooks and so on. And what they do is they put a kind of jar on it, right? And in very short time, the candle goes off. And when the candle goes off, the water level goes up. Water level here is here, and inside the jar it is like that. So if you measure the difference between this height, this and this, you will see that this is 1/5 of this. Conclusion, this is what the textbook says. Air is composed of oxygen and other things. Oxygen is 1/5 of the air, and the candle flame eats up all the oxygen, so that means 1/5 of the air is missing, so the level goes up, right? And everybody accepts it. Okay, now here's a 15-year-old who says, the 15-year-old asks the teacher, how is this oxygen used up? This oxygen in the air combines with carbon in the candle and produces carbon dioxide. Where is that carbon dioxide going? Back into the space, right? So oxygen is not absorbed, oxygen is put back into the jar, but along with oxygen is also carbon. So shouldn't the level go down? Because there is additional carbon here. Did you get my question? It is not the case that the candle flame has absorbed all the oxygen. Candle flame has combined oxygen with carbon and produced carbon dioxide, and the carbon dioxide is in here. So there is more material here. Wouldn't you expect the level to go down instead of go up? Why is the level going up then? What answer would you give to our 15-year-old? This is all over the place. Any YouTube video will give you this. Any textbook will give you this. What are you going to do? Of course, you can say, shut up and learn this stuff. If you do not want to do that, if you want to respect the intelligence of the 15-year-old, what answer would you give? Of course, there is one possibility, because you may not be able to answer all the questions that 15-year-olds ask. You can say, I don't know. Perfectly good answer. You should have the courage to tell your students, I don't know. That's the very first step. But that is not sufficient. You should also say, I will try to find out. And how will you find out? There are two options. One, you can read it up somewhere. You may not find it. If you read up many of these questions, you may not find answers on the internet. You'll have to think about this on your own. You will have to exercise your mind than getting the answer from somewhere and giving the answer to the students. That is where inquiry comes in. Okay, so what's your answer now? Why is the water going up, the water level going up instead of going down? What's your answer? I assume that I'm a 15-year-old. What are you going to tell me? Yeah? Okay, you will say you don't know. How many other people would say I don't know? Raise your hands. Okay, not everybody has raised their hands. Anybody who hasn't raised? Huh?
The size is different.
The what?
The size of the oxygen and CO2, maybe CO2 is more, so the space will be
The what is not? What is different?
the size of the CO2 and oxygen.
Size, you see, a carbon dioxide molecule is composed of one atom of carbon and CO2, right? 2 atoms of oxygen. How can the size of one atom oxygen be bigger than the carbon dioxide molecule? So if you say that answer, size is different, your student is going to ask you the same question. How can carbon dioxide molecules be less size than the oxygen atom? So that's going to put you in trouble. So I would suggest that you opt for I don't know answer. And it will take some time for you to think. At least, I would say at least a few hours. This is not something that you can answer immediately. Anything that you can answer immediately, you have memorized it. Thinking requires time. Thinking is not something that you can do in 2 minutes. Like, for example, the multiple choice questions that you come across, which you have to answer in less than 2 minutes. Have you done that? Before you came to the Department of Education, students, did you have to go through this test? No, you did not. Okay, many programs require that you do the multiple choice answer, everything in 2 minutes, less than 2 minutes, some in even 1 minute. And the idea of giving you 1 minute or 2 minute answers, questions, is to make sure that you're not capable of thinking. So you have to be filtered out. If you're a thinking person, you're dangerous. So the system of education does a good way of filtering out thinking people by giving multiple choice questions. If I took the multiple choice question for my own subject, linguistics, I won't get more than 10 marks. I'm glad that I lived in a time when there were no multiple choice questions. Okay. From this, I take just one more question. Many of you have specialized in social science, I assume, right?
English and social
Right?
science. English, social science, natural science. 6 subjects are here, sir.
I'm sorry?
6 subjects. Commerce.
6
social-
subjects, commerce.
Social science, natural science, physical science, English,
Yeah.
maths.
So natural science is physics, physical sciences and biological sciences.
Natural science, biological, botany and zoology.
Botany and zoology.
Physical science, chemistry and physics. Chemistry and physics.
Chemistry and physics. Astronomy is social science.
No, astronomy is.
No? I thought
Physics, astronomy is very physics.
I
Physical
thought
science.
the solar system was discussed in the geography chapter. Geography is social science.
Yes.
Therefore, astronomy is social science. Right? Yes or no? You like the idea that astronomy is social science?
Physics and social science.
It's a science about the society of planets. Of course, I'm just kidding. Yeah. So there's a division between natural science and social science. Social sciences are not natural; they're unnatural. What's the basis for saying study of human beings is not natural?
Study of human beings in natural science, that is, so it comes under zoology, so we
Because it
consider-
comes. But we also said that humans are animals. The study of animals is biology, right? Zoology.
zoology.
Yeah. And how come you accept this idea that social sciences are not natural sciences?
Behavior.
Huh? Behavior?
It's human behaviors, social science.
Yes, human sciences, yes. I'm asking the question about social sciences.
Social relationship.
What is it?
Social relations, you have social relations among bees, among ants,
Social
among chimpanzees, but these things are taught by biologists, not by
Human relationship.
human. Of course, the important part is the human, right? So there are people who are studying behavior of bees, social behavior of bees, and people who are studying human behavior. And social science means human sciences, relationship. Yeah. What is social about psychology? Psychology is study of mind.
Yeah.
There is nothing about sociology in psychology. Also, psychology is social, but psychiatry which is also about human mind. Right? Psychiatry is natural science. Psychology, which provides the theory, is unnatural. Pretty strange, isn't it? And this is what you have been studying in schools and colleges. So I start asking these questions. Why is psychology treated as a social science, but psychiatry is treated as a natural science? Pardon me? Yeah, that's right. Exactly. Somebody decided that psychology is not, is not a science.
So now psychology is also considered a science. MSc psychology is
Pardon me?
MSc psychology is also.
MSc in psychology. Exactly.
And MA in psychology and also MSc in psychology.
Is there a difference between the two?
No, I don't know, sir, actually.
Yeah, I have before I did my PhD, I decided to have a master's degree in linguistics. I was studying part of the PhD program in MIT, and I decided if I want to come back to India, I need a master's degree, otherwise I won't get a job. So I asked the department for a master's degree as well. So they gave me an MS degree, Master of Science in Linguistics. But if I come to India, Master of Science in Linguistics, no, but linguistics is a social science. I should get an MA degree. How come MIT decided that this was a science, and most Indian universities decide that linguistics is a social science? I do nothing about society, by the way. The kind of linguistics that I do is the study of language as part of the mind. It's what we call a cognitive science, not a social science. Okay, all this was to give you a feel for questioning what we take for granted. That's the title. And there are other things. I obviously will not have time to go through all the questions, so I'm going to pick a few things at random. You can ask me to go through some of the other questions if you feel like. Okay. Okay, this is my favorite question. On the next slide, distinction between solid and liquid. You learned this in primary school, right? Solid and liquid? Yes. And this is what you must have done. Solid has both shape and volume. Liquid has only volume, no shape. Okay? So what that means is, if something has shape, it is solid. But so a liquid, for example, acquires its shape in a container, right? So if you take a glass of water and put it in a cylindrical vessel, it will have cylindrical shape and so on. Everybody knows that. Very simple. Okay. Now, you take a grain of wheat. You take a grain of wheat, it has its own shape and volume. Obviously, a grain of wheat is solid. You take a handful of wheat and put it in a glass. Does it take the shape of the container? You change the shape of the container, it takes the shape of the container, right? So, according to the definition given to you, one grain of wheat is solid, but a handful of wheat is liquid. Another conclusion, you take a sewing thread, let's say 10 meters long sewing thread, put it in a container. Does it take the shape of the container? The shape of the thread will depend upon the container, right? Conclusion, sewing thread is liquid. Soap bubble, what's the shape? Spherical. Soap bubble is solid. Are you sufficiently uncomfortable? So this is what is happening. Your own intuition, the answer that you have, you would like to classify handful of grain as solid, sewing thread as solid, but soap bubble as liquid. But the conclusion arising from the textbook definition logically contradicts your intuitive answer. I don't care which answer you accept, but you can accept only the textbook definition or your current belief. What would you choose to do? Do you want to accept the idea that a handful of wheat is liquid? Yes or no? Raise your hands. How many people for yes? And how many for no? Okay, number of hands went up, others are still thinking. Here is the problem. If you accept the idea that a handful of wheat is solid, then you cannot accept the textbook definition because the conclusion arising from that is logically contradictory to your current belief. You cannot accept logical contradictions. So that means you must reject the textbook answer. You don't have a choice. So are you happy to reject textbook answers? I know the anguish that you're going through, and that was intended. Learning is not easy. Meaningful learning creates exactly that kind of anxiety and anguish, and better face it. You have to give up some of your favorite ideas, some of the things that you're absolutely certain about. That's part of your learning. But this is not enough. It is not enough to reject the textbook definition. You now have to come up with your own definition, a better definition. And I'm pretty sure that you at this point, if I ask you, you will not be able to come up with a definition. But I suggest that you take your time when you go home, try to come up with a definition, talk to your friends. Right? And if you want to write to me, my email address is at the end of this thing. Feel free. And again, I promise, I don't bite people through my emails. You're perfectly safe. Okay, one more example of the logical contradiction problem. And also the need to subject not only political science and history and philosophy to critical thinking, but also to subject physics and mathematics textbooks to critical thinking. You know what a straight angle is? You know what a right angle is, acute angle is, straight angle is. What's a straight angle? 180 degrees. Okay. So in other words, if you have a line AB, a straight line, and you put a point C on it, this angle is 180 degrees. That's a straight angle. Right? Straightforward. This you learn, I don't know, 6th grade, 7th grade school textbook. You also learned that you can put a point anywhere, right? Randomly.
Yes.
How many straight angles are there in any finite line segment AB? Yeah? Infinitely many, right? You can put randomly, and Euclid says that points have no size. So there can be infinitely many points in a finite line. And therefore, infinitely many straight angles on one finite line. Okay? Keep that in your mind. There are infinitely many straight angles on a finite line segment. Ready? Okay. So here's a triangle. A, B, C. Each line segment has infinitely many points and therefore infinitely many straight angles, 180 degrees. What is the sum of all these angles?
180.
Infinitely many. What did you learn in your text? Okay, what do you want to reject? The textbook answer or your answer? You choose. Either way, you are in big trouble. Any solution to get out of this problem? If a school student or a college student raises this issue, I know how to give an answer. It's very simple. Am I going to share that answer with you? No. Because my idea is not giving you what I know, but helping you to think on your own and develop your mental abilities. If I give you the answer, you're not going to learn anything. You just acquire a piece of information, which can be tested in a 2-minute multiple choice question. That's not valuable learning. So will you try to find out? I'll give you a clue. Usually, I'm not compassionate, but on today's Wednesday, right? Today's Wednesday. On Wednesdays, I'm compassionate. So I'll give you a clue. You may have heard this word, angle, and you may have heard this word, vertex. You familiar with that word in geometry? Okay. If you carefully think about the use of the word vertex, you can come up with a good answer, which does not involve logical contradiction. Of course, that would mean still rewriting the textbook, but not in such a dramatic way. Okay. That's all that my compassion allows me to do. That's a clue. That one, unless you, at the end of the session, you ask questions, I'm going to skip that. What's a straight line and so on. What's a straight? Yeah. Actually, that is related to this question that I raised just now. If you have two straight lines, again, I'm asking questions about what you learned in primary school. If you have two straight lines, they can intersect, right? Can they intersect at two different places? No. Okay? This is the assumption that Euclid made. This is almost, you can treat it almost like an axiom. That is, this is part of Euclidean geometry. There are other kinds of geometries. Euclidean geometry is a geometry of flat surfaces. There are other kinds of geometries, I don't know if you've heard about them, called spherical geometry. You've heard about them. Okay? Spherical geometry is what Einstein used for his relativity theory. Without spherical geometry, you will not be able to calculate whatever it is, the GPS system that you have on your computer. You can't without Einstein's theory of gravity and stuff like that, and spherical geometry. In spherical geometry, instead of assuming that no two straight lines can intersect at two different points, you assume that any two straight lines intersect twice. That's an axiom of spherical geometry. Completely opposite of Euclid. But there is no logical contradiction between the two because they were talking about two different worlds. In a flat world, Euclid's axioms hold. In a spherical world, spherical geometry's axioms hold. So there's no contradiction as long as they are between. So what mathematicians do is to imagine these worlds. Okay? So imagine a spherical world. And let us inhabit this world with creatures called triangles and lines and points. And they study those worlds and those inhabitants and come up with theorems. That's what they do. Scientists study the world that we live in. Mathematicians, on the other hand, study logically possible imagined worlds. And if you ask a pure mathematician, is the world that we live in, is it Euclidean world or the non-Euclidean world? I don't care. I just construct these theories. But there was a mathematician who did say, yes, spherical geometry is actually as interesting as Euclidean geometry, but the world that we live in is Euclidean. Now, in saying that the world that we live in is Euclidean, he was actually behaving like a scientist, not like a mathematician. This was a great mathematician called Poincaré. And he said this at the beginning of the 20th century. Just a few years later, Einstein established his theory of relativity. With that, the idea that space is, governed by spherical geometry. So Poincaré was wrong. Great, one of the greatest mathematicians of the 20th century. Einstein, one of the greatest scientists of the 20th century. One proves the other one wrong. This is part of academic knowledge. Okay. The pursuit of academic knowledge cannot happen unless you are willing to be proven wrong, unless you are willing to prove others wrong. It doesn't matter how great you are. That's a crucial part. Okay, so if you accept spherical geometry, right, it follows that any two straight lines must meet, intersect twice. And to understand the intuition, it's easy. Okay, take a globe or take a Mozambique, reasonably spherical. How do you draw a straight line on it? There are two ways of drawing a straight line. One is the shortest path principle, to take a string and stretch it tightly, and from two different poles, that's a straight line. But you can draw many such straight lines, right? The longitudes. And any two longitudes intersect twice. That's the idea of spherical geometry. Okay? And let me ask you a little more difficult question. On a spherical surface, what is the sum of angles? Is it 180 degrees, more than 180 degrees? Can you have a triangle in this spherical world in which the sum of angles is not 180 but 270? There are three right angles in a triangle, in a spherical world. Okay? Now, this time I'm going to tell you, I can prove it to you, that there exist triangles that are three right angles in a triangle. So the sum of angles is 170. I can prove it to you, but I will not do so now, for obvious reasons. Because if I don't tell you what the proof is, you're going to be very uncomfortable. My goal is to create that discomfort. Okay, let me skip. Okay, you must have learned that light is a ray. You must also have learned that light is a wave and light is a particle. You learned all this stuff. Is light all of these? If light is a ray, a ray is a straight line with an arrow at the end. How can it be a wave? Wave is like this, straight line is like this. How can light be both a ray and a wave? And if it's a wave, how can it be a point? I mean a particle. What was your idea of light when you were children, before you went to school? What did you think of as light? So at night, you cannot see anything. You turn the light switch on, light fills the room and you can see. What is the thing that fills the room? Is that a ray? What was your early idea? Light fills the room, right? So light is a kind of substance. So your early idea when you were children was light is a substance, and your teacher in your textbook tells you, no, you're wrong. It is not a substance. It's a ray, and the teacher then tells you it's a particle and it's a wave, and you accept all that stuff, completely logically contradictory. This worried physicists in the 19th century. There was a wave theory of light and particle theory of light. And there was a logical contradiction. It may not worry textbook writers, but it did worry physicists. The contradiction between the two. And they resolved it much later in the 20th century. You can find out how they resolved it on your own. Do a Google search. You may not fully understand it. It doesn't matter. At least you can make an attempt. And interestingly, there was evidence for both. There was evidence for wave theory of light, and there was evidence for particle theory of light. So that was difficult. How do you integrate these two things? So that is conceptualizing. You have to move from the conceptualization of light as a substance to ray, to particle, to wave, and none of those. The current stuff is none of those. But that progression from your experiential knowledge as a child to your rational academic knowledge as a student of physics, undergraduate degree, bachelor's degree in physics, is a huge path. It's not easy to traverse that. And quite often what happens, your textbook doesn't tell you how to move from experiential knowledge to academic knowledge. So you tend to repeat whatever words you hear without understanding. That is very sad. You don't have to do that. You can help young children move from their experiential knowledge to academic knowledge if you give them the reasons in ways that they can understand. Okay, I'm not going to go through this one. This is related to the question that I asked earlier, the Earth going around the Sun versus the Sun going around the Earth. Incidentally, you can use either of these theories, what is called the heliocentric theory, where you say Earth goes around the Sun, or the geocentric theory, where you say the Sun goes around the Earth. You can use either of those theories and explain this. Both theories can explain. The question would be, then why did you reject the geocentric theory? Okay. We did this in a workshop with 8th grade children who, when they began, were absolutely certain that the geocentric theory was wrong, because that's what the textbook said. We made them construct the geocentric theory, explain phenomena, and they did an excellent job. So all the phenomena that we pointed out, they explained. Of course, it needed considerable guidance, but they did it. And then we made them construct the heliocentric theory. The heliocentric theory also explained it. So one of the kids said, if both theories can explain these phenomena, why did you decide that the geocentric theory was wrong? And all the kids said, yes, why? Why did we accept that one? So we smiled and said, we are not going to tell you. We did not. For a whole day, we gave no answer at all. And the next day, we pointed to a few things. Said, if you pay attention to some of those clues, we just gave them clues. And then they'll be able to figure out why we reject the geocentric theory and reject, what did I say? Why we reject the geocentric theory and accept the heliocentric theory. The kids came up with arguments. And they understood the stuff much better than most physics students, astronomy students. You need to understand these arguments. Okay, I will just give you one more question, which I will not discuss here in the class, but this is your homework. Okay. Suppose the state government, Kerala state government, decides that there should be a course on critical thinking and inquiry that all bachelor students should take. Okay. And the government appoints a committee to design a first-year foundation course on inquiry and critical thinking. And they decide you are going to be members of the committee, the people who are sitting in front of you. Okay? You have maybe a year, 2 years to figure out how to construct that foundation course. Right? Write a proposal, let's say in a 1 page or 2 pages, how you're going to create that foundation course. Take your time. Okay? So talk to your friends, talk to everybody you can think of. You can work in groups if you want, and say you can form teams of 3 or 4 or 5. And send me a proposal. You have my Gmail ID. Where? Somewhere here. Yeah, okay, the last page, the last slide, I have given my Gmail ID. If you send me a proposal in the next 1 month or so, okay, then I will take this session to have been successful. If I don't get any answers from you, I would join my wife and be extremely sad that nothing really happened. And you don't want to make two of us sad, all right? Okay, so incidentally, you can also use the other. I have given you lots and lots of other. So if you go to the Think website, yeah, you'll find lots of similar tasks: exposition, videos, PDF files, whole bunch of stuff that you can download and learn from. You might at least watch the first one, Systematic Destruction of the Thinking Capacity. It's a 2-minute video that tells you how to destroy children's minds. You might find it amusing. It's amusing at one level, but it is extremely sad at another level, because this is what is happening. Okay, so I leave the remaining 15 minutes to your questions. Or comments, questions, comments, feedback, whatever you want to say. And convince me that you are alive mentally. I'm going to sit here and wait for comments.
Actually, really.
Yeah. You can sit there, yeah.
Actually, this session is really something new for us. We have never participated this type of session. All of us are very glad to be here, sir. Thank you very much.
Okay.
And my question is, while we considering all these points or concepts, how can we develop a curriculum for primary school students? We will start all these things from the primary level. And what are the measures we have to take while we are constructing a curriculum for primary students?
That is a difficult question for me, because you see, my experience has been from PhD program. So I was teaching PhD students in US, and I hadn't taught undergraduate students. When I came to India, when I came to Singapore, I had to teach undergraduate students, bachelor students. And it was a very difficult job for me, because the strategies were not work for undergraduate students. But I learned how to teach undergraduate students after 2 or 3 years of hard work. And then when I came to India, people said, you have to begin, in secondary school. And I was terrified, because I had no experience of teaching secondary school children. But there's a mathematician in Institute of Mathematics, Chennai. His name is Ramanujan. Well, he was in Chennai Mathematics Institute. He's now in APU, Simple University. We are good friends. And he said, look, you can't do any of this stuff unless you have the experience of teaching secondary school kids. So go to a school, be part of the community, and teach a course. At least be there for a year. Otherwise, everything that you're saying is up in the air. You have no experience whatsoever. So I thought about it, and one school was willing to, for us to try. And we introduced this course on inquiry and critical thinking for the secondary school. And I bid for 8th grade. Because 8th grade, I thought, I can manage. And they said no, 6th grade. And I was terrified. 6th graders are not, they're Martians, okay, and they're not quite human. So I'm terrified of little kids. But finally, I had to yield, and I said, okay, 6th grade. And I did manage that with all my anxiety, all my fear. Not just me, there were other people with me, and they gave me hints, and the teachers also gave me hints. So we did it together, and that course was successful, and we did 2 or 3 years. And then Another teacher, a principal from that, said, how about the second grade? And I said, no way. That I was absolutely certain I would not be able to. Second grade kids are like what? 8-year-olds? 7-year-olds? Yeah. And my grandson is 8-year-old. Will I teach a group of kids who are his age? No way. Absolutely not. But my wife did it. She taught for a whole semester. So the reason why I'm saying this is because I'm terrified to teach primary school kids. There are limits to what you can do. Since I have no experience of teaching those kids, I cannot directly answer your question. But I can give you, if I had that ability, then this is what I would do. I would not teach them anything. Instead, I would engage them with activities that they think are just they're playing. They would not realize they are learning anything. So here are some possible activities. I would teach them origami. Okay? By doing origami, they don't realize that they're learning geometry. Incredible geometry. Okay? So yeah, I'm preparing the ground for learning geometry in secondary school. I would teach them to play with shadows. So for example, I can take a ball and the shadow will increase its size or decrease its size. I can take a cube and do the same thing, but the cube will also change its shape. So if it's a Coke can, I can make a circular shadow and a cylindrical shadow. But I can't do that with a cube. How come? So, I can introduce all these questions while we are playing with shadows. They are playing with shadows, but what they are learning is actually projected geometry. Okay. I will teach them. No, I will not teach them. My wife will teach them knitting and crocheting. I don't know what the difference is. Crocheting is done with one needle and knitting is done with 2 needles. But it's amazing geometry called topology. If you have had the experience of doing knitting and crocheting, you can understand topology much better. And these people have discovered that when they learn topology in their undergraduate program, girls are much better than boys. Why? Because girls have learned knitting and crocheting, boys haven't. Boys are at loss. They don't understand it. Which is a good thing, because people think that boys are better than girls in math. Not really. It's a kind of initial learning experience. And there are many such things. So I will teach them farming, gardening, cooking, all this comes with biology and chemistry can be learned through these activities. So if you have a rich experiential basis to teach all these other things, that is the best way of designing a primary school curriculum. If you would like to do that, I can help you seriously. I cannot do the teaching, but I can help you suggestions and stuff like that. I'm not able to teach primary school kids. I can also get others who are interested. So that was a kind of indirect, lengthy answer. I'm best at places like this, higher education.
Sir, I'll ask you that question because that everything if we start from the grassroots level, that is why I'm asking that question. Okay.
Yeah, but it's not necessary that something like reform in education should start with primary school. Here is why. See, who are the primary school kids? Primary school teachers. They have an educational system. Maybe they also have undergraduate degrees. But if they don't have good education at the undergraduate bachelor's level, how can they teach? They are also the victims of the same system of education. And it's easier to, the way I see it, it's easier to manage university education. Not even affiliated colleges, because university education, the number of teachers, number of students is much smaller. And if you start there is a hope that it can spread to affiliated colleges later. And then those who are educated will then become primary school teachers, secondary school teachers. That way education will change. But if you begin with primary school, the size is so huge that I cannot even begin to imagine what I will do. You can try a little bit in individual schools to see what is possible. But we cannot implement that at the national level or even at the state level. It's impossible.
Thanks.
How many participants are mentally alive?
25 are mentally alive, sir.
How do I know that? I don't see indications of that. So I'm not going to believe anything that, I can't see evidence for.
Sir,
Yeah?
now,
You don't have to stand up, but if you feel like, that's okay. But loud enough, I think, yeah.
sir, India is much advanced now, and how can you say that we can't believe that those recordings of this researchers, scholars as evidence? How can you say that it is not an evidence?
Okay, because if you ask that question to a serious scientist, for example, like Richard Feynman, Einstein, people of that caliber, they will say, nothing that we know in science is completely certain, number one. This is repeatedly stated by the best leaders of science, and even mathematics actually, not just science. And they also say, it is for us to progress, it is important to correct the existing body of knowledge, to challenge the existing body of knowledge and correct it. So it is important that we ask that question, how do you know that? So that we can correct the existing body of knowledge. Not only that, we will empower our students later to become scientists and correct their predecessors. If you look at the history of science, you find that this is so, systematically. For instance, Newton thought that time and space were not related, they did not interact with each other. Einstein showed that if his theory were right, Newton was wrong. Okay? Prior to Dalton, people didn't believe in atoms. And Dalton proved that his predecessors were wrong, that substances are made out of indivisible particles that they call atoms. Atoms are indivisible. And that theory became accepted, and so much later, well, very soon, people discovered that atoms are divisible. So Dalton was wrong. And they said, okay, atoms are made up of this indivisible particle called nucleus, and the electrons are stuck on it like bugs. That turned out to be wrong. People discovered electrons are not stuck on the nucleus, they kind of orbit around the nucleus, but nucleus is indivisible. That turned out to be wrong. Nucleus is made up of protons and neutrons, but these are not divisible. Notice the history of atomic theory is a history of the mistakes that scientists made. What is the guarantee that 50 years from now, or even 20 years from now, people would not discover that electrons are also divisible? So we must take that attitude that everything that we know today is subject to doubting and questioning, and everything that we know today is fallible in the sense likely to be a mistake. But until somebody proves that it's a mistake, we'll tentatively accept it as true. And that's the scientific temper. Tentative acceptance. Not with absolute certainty, but reasonable certainty. So I'm not saying that all the scientists today are wrong. I'm saying they are not infallible. So we must doubt and question them. Yeah.
Sir, these this kind of critical thinking, if the ability, will that ability be subjective to like kids who are like gifted children, or is it like subjective to kids who are like
Subjective?
to kids who are like gifted in some way? Are like, will they be only asking these type of like questions in classes generally, or is it like
Okay. My experience has been that young kids are extremely creative and they love critical thinking. They like questioning, doubting, these kinds of questions. But as they grow older and they're in this institutional setup, what happens is that natural inquiry abilities and critical thinking abilities of children are curbed by the system. The system does not allow them. Okay? So take for example the language. Children have a natural ability to absorb languages. They don't have to be taught. All you have to do is to expose them to a language. They'll pick it up in no time. But are they ever given a chance to speak what they think? When a teacher asks a question, they're not looking for what the students think. They are supposed to give the answers that teachers want. So to the extent that in some of the studies that we conducted, one scientist asked a kid, a 6th grader, 8th grader, I'm not sure, so what do you think? And she said, what I think is irrelevant. What is the correct answer? That's what I want to know. And the scientist was totally surprised by the answer, what I think is relevant, because he was trying to get them to think and speak that. And the kid, when the scientist probed further, he discovered the children thought that their job was to learn what is there in the textbook and repeat it, not really talk about what they think, because what they think is obviously wrong. So the habit of saying what the others have told to them destroys their language ability. Instead, if you listen to them and get them to articulate their thoughts, this is what a program called Philosophy for Children is doing. Incidentally, this is part of the answer to your question. You can do a video YouTube search for Philosophy for Children. They teach philosophy to, let's say, 2nd graders, 3rd graders, primary school kids. And it's amazing. They don't tell, the Philosophy for Children is not a program to teach them what Plato said, what Hume said, what Aristotle said. No, but thinking like a philosopher. So they take experiential things in life and gives learners a chance to express their ideas, come up with definitions, engage in debates and so on. And you can see that the intellectual maturity of the primary school kids is far greater than the intellectual maturity of PhD students. It's amazing. You should watch those videos. So that's definitely the best way of doing it. As long as you don't destroy their thinking abilities, they are in good shape. But you can go beyond that and say, nurture them.
So can we add that in the curriculum, like during examinations? Can we add an open-ended question for them to explore their ideas? Will it be possible to add in science also?
That was my the final assignment, that assignment. So I cannot give you an answer to that one. But I can give you a clue. I think yes. But you have to come up with a proposal. Yeah. So let me ask you one simple question. I asked you to construct that proposal, but suppose we did that. It's not enough that we do it, you should also do it. Suppose we came up with a proposal and we created that course, the textbook and videos and everything, including assessment. Of course, it has to be assessment that allows students to answer questions, gives you at least 10 to 15 minutes. Okay? And it is possible to create that kind of assessment, even computer gradable assessment. I can show you how that can be done. Do you think it is feasible to set that up for bachelor students in Kerala? As students, what is your subjective response to that? Is it feasible?
I think yes.
Using exercises of this kind?
I I think at the beginning stage it will be very new and people won't be like students in special won't be very supportive to that, and they feel like there will be biased evaluations and all because there won't be strict criteria of answering and all.
Okay.
But later on, I think they are going to see the positive influence that happened on them and they are going to accept that system.
Okay.
Maybe in a long term, it might be.
So what is the fear of subjective evaluation? If it is computer graded, not teacher graded, computer grades you, then there is no subjective biases, right?
If it's like a descriptive answer, how it is possible to evaluate?
I can give you detailed answers, but if you write to me, I can send you a paper that I wrote for current science. The basic idea is this: replace the existing MCQs with 5 options with MCQs with 20 options. Okay, that's the first step. Second, the answer should be based on something new that they're given, let's say a half-page write-up or one-page write-up. So they have to learn how to read. 2, there is no one correct answer. To get full marks, you will need, let's say, 5 ticks. But it may be 5, it may be 4, it may be none, it may be 15. We don't know. So you have to exercise your judgment to decide which ticks, which options you're ticking. And those things will require serious thinking and reasoning. So at least 15 minutes to 20, 25, even 30 minutes, you will have to give the student, not 2 minutes. 2 minutes you cannot test anything. This is the nearest to a descriptive answer, what they call open, ill-structured questions and so on, open questions. It is possible to do that in terms of computer gradable questions. But it is still not going to be like an interview. But this is the best we can get, and we have to restrict ourselves to what can be done through that means, and it is doable. And of course, there will still be dangers because if that is set up, all the coaching companies will be up in arms because they wouldn't be able to deal with these questions. But that will be a political, economic struggle. I don't know what to do with that. But if there are ways of taking care of the coaching companies, it is doable. Any other questions? Okay, so does this mean that about 24% of the sample sitting in front of me are mentally alive, and what about the others? Should I conclude that the rest are not mentally alive or they are afraid? Oh, sorry. Okay, 24.
So the thing is that what I have learned from this is the major prerequisite is that a basic foundation of physics or chemistry, basically scientific knowledge.
No, not scientific knowledge.
I mean, like in the candlelight experiment or.
Yeah, I gave some examples
maybe,
of that, but if you look through this, you will find that it covers just about all subjects. For example, it includes political science, it includes history, it includes philosophy. This has no subject. So here's an example. I raised this question about defining triangles. That can be moved to defining solidity. That can be moved to defining, let us say, democracy. That can be moved to defining knowledge. That can be moved to defining civilizations in history or golden age. All those things. The activity of defining does not know subject boundaries. The activity of classifying does not know subject boundaries. The activity of reasoning does not know subject boundaries. So what you learn in one subject automatically is moved to all the other subjects. But of course, you should also take different subjects for the variety. So that's what we do. We take examples from all possible subjects. Yeah. Including, for example, forensic reasoning and reasoning in the law court, reasoning by, for example, medical doctors in diagnosing a disease, all those things. Examples of causal reasoning.
we have an accrued wisdom on us. And sometimes the linear development of the language activity and tools used for example, what I mean is math like a child may not be able to ask a question.
Oh, sorry.
Child may not be able to ask a question, which is possible today for a specialist, thanks to the mathematical language developed by it's part of the accrued knowledge. And so take physics for example. Today, if you just leave children, they may at the best go up to mechanics, because that's what they will be able to identify. But to quantum mechanics, they need a lot of abstraction and issues like quantum entanglement or quantum coherence. All these require a major rupture, but at the same time, it requires a totally different language for doing knowledge and communicating.
Yeah. Yeah, so I think my answer to your question would be something like this. To get to quantum mechanics, we need several preparatory strands. So for example, you need geometry, various kinds of geometry, from Euclidean geometry to spherical geometry and other kinds of things. Even discrete geometry, where you assume that a finite line is made up of a finite number of points. This is one idea that many physicists are pushing now in what they call discrete causal logic. Now, to prepare students for that and assume that quantum mechanics is taught in the 4th year of their bachelor's program, not before that. How do you prepare students to get there? We begin with geometry as science, not as mathematics. So triangles and rectangles and so on are not mathematical objects. They are objects that you can draw on a piece of paper or cut out with a piece of cardboard. And they investigated like science. And this is what can be done at the primary school level. At the secondary school level, you can teach them geometry of Euclidean kind, where lines are invisible, points are invisible. It's a huge, change of mindset, because young children think that lines are things that you can draw on paper. And when Euclid says, no, you cannot see, lines are invisible, you cannot see them, it's very difficult for children to conceptualize it. And I have tried this with kids, and it requires at least the onset of teenage to understand the idea of invisible lines and to grapple with that kind of stuff. And then you teach them also Euclidean reasoning without equations. Euclid reasoned with language. If you teach them algebraic reasoning, like f is equal to ma, you are hindering their progress. Let them learn to reason using whatever language they have, whether it is English or Malayalam or Swahili, doesn't matter. It is best to use borrowed English words. So don't use words like Trikonam and Chatushkon. I don't know what their translations are. Pancha. Yeah. Okay. Why not use English words? I mean, Malayalam has borrowed all those words like what do you call this? Mobile, right? It's not Malayalam. And just about all the words that kids now know are English words. Why not use English words for that? It will still be in Malayalam. They learn to reason, they learn to think in Malayalam. Of course, side by side with that, they also learn English as a separate. And the reasoning that they learn is not restricted to English or Malayalam. It will be above the language level. Then you teach them how to reason with the formal equations. Only after they have learned reasoning very well with language, academic language, then you move to algebraic formal reasoning. And I would begin with formal logics rather than, algebra. because the formalism of formal logic is much easier to handle then. But even for that, I would teach them first ordinary reasoning in ordinary language, and then formal logic, different kinds of formal logics. If that is done, and you also do some evolution of physics along the lines done in Einstein and Felsberg, they will be ready for quantum logic at the bachelor's, fourth year level or master's level, I'm not sure. There is no point in teaching them quantum mechanics unless they learn to conceptualize the world differently. So there is something called quantum logic. If you don't understand quantum logic, then quantum mechanics, part of the quantum mechanics may be ununderstandable. And I don't think right now people understand. Entanglement is another case, okay, where Einstein was proved wrong. Okay, so to understand why Einstein was wrong, you need a lot of preparation. But I think it is feasible if you take small steps to develop students' minds. And by the way, so-called quantum logic was initially proposed not as quantum logic, but with the name Chatush. This was invented by Nagarjuna, the Buddhist philosopher. It's an amazing system, and that's what quantum mechanics is using. And for them to discover that this was proposed by somebody who didn't even know quantum mechanics, of course, not even classical mechanics, but he had that idea of a different kind of logic. So if you bring in all these different strands moving up to quantum mechanics and relativity, then I think physics graduates would understand physics. Right now, I was a physics graduate. I had no idea whatsoever what physics was. And I hated physics intensely. I cut all my classes. I learned my physics here at University College. I went there. Yeah, where is University College? And one thing I did was cut all my classes because it didn't make any sense to me. They taught me how to measure the Vernier calipers and this and that, and it didn't make any sense to me. They asked me to go to the lab and do experiments. I copied my sister's lab reports and gave to them. And instead I went to the public library and read other things. And all my learning was from the library, not from the classes. And I think my physics teachers hated me. And I hated them too. And I understood what physics was for the first time in my life after my PhD in linguistics, when I read Einstein and Evolution of Physics. I said, whoa, so that is physics, I didn't know. So if I had read Einstein when I was a bachelor's student in University College, I would have become a physicist instead. Because I didn't know what physics was. The same thing happened to me with mathematics. I learned to solve problems and equations and all that stuff. I also remember learning Pythagoras theorem. I could do the proof. Meaningless stuff, of course. I liked it. I liked playing with symbols. And then I read, after my PhD in linguistics, I read Concepts in Modern Mathematics by Ian Stewart. I recommend very strongly that book. It doesn't give you formalisms, equations. It teaches you concepts. And I saw the proof of Pythagoras theorem that in terms of picture, in terms of a diagram, which apparently was Indian mathematician. What's the name of his daughter? There, the Lilavati. It's not clear whether the proof was the fathers or the daughters. I don't know. But anyway, it comes from him. And I looked at that picture and said, oh, so that is Pythagoras theorem. I didn't know. With all the proof that I had learned in my undergraduate days. And that is when my understanding of mathematics started, my understanding of physics started. So, most of it happened outside of classrooms and textbooks. So it's one of the reasons why I am into this now is to avoid my fate as a bachelor student to the existing students. If that can be changed, if the so-called mathophobics can be converted into mathophilics. Mathophobics think math is meaningless, terrible, they have no capacity for math, but most of the mathophobics that I have interacted with love math actually, and they have high level of thinking capacity in math. And the reason why they think they are no good at mathematics is because they are taught to calculate and are not allowed to think. That, of course, is a terrible thing to do. So, if you give students a chance to understand real mathematics and real science and so on, you can change things. And this is what I would like to do, so that the kind of horrible practices that I was subjected to would not continue to happen in the classrooms.
Although generally we say that it's curiosity process.
It should be. Yeah. Yeah. Yeah.
But there is, I don't want to say hierarchy, but knowledge, we take the whole corpus history of knowledge collection. Curiosity alone will not help, because curiosity will initiate certain questions, but constituents of questions are drawn from a certain level of knowledge. That's why I said children will be able to understand mechanics because their questions will be of that kind. But at a very late stage, several curiosity-driven investigations, exercises, generated knowledge, and that level of knowledge would provide constituents for the making of questions.
Yes, I agree. So at each level, you ask questions at that level, and that gives you curiosity. In fact, kids will also be asking questions at that level. So it doesn't make sense to, for example, talk to secondary school students about emergence. That's an abstract concept. But a biology student, bachelor's student, can understand the question that was asked in the book, What is Life? Schrodinger.
Sure.
So you give them Schrodinger's article, and that suddenly creates a lot of curiosity, but only when they're ready for Schrodinger, not for that. And that is, I would say, something like second year bachelor's in biology. I'm not sure exactly. I mean, this year to find out what the appropriate level is. And same thing with, for example, okay, let me try this out on you. I'm trying to take an example from a book called Phantoms in the Brain. Have you read that? No, good. So there is a brain illness called Capgras syndrome. The spelling doesn't matter, it's CAPRASS. This is because of a brain lesion. Okay, some brain impairment because of a stroke or some falling or something like that. And the patient who has this Capgras syndrome believes that some of the things that he's very close to, like his parents or a pet, is an imposter. So the patient would say, that is not my father, he looks exactly like my father, talks like my father, but it's not my father, it's an imposter. So it's mystifying why they say this. What is more interesting is when they hear their father's voice in some other room. Okay. So that's my father. Then they open the door, look at the father and say, that's not my father, that's an imposter. Why do they do this? How come the auditory stimulus gives him the idea of his father, but the moment you have visual stimulus, then they say, that's not my father. Okay. Now, we have tried this in the first year bachelor's courses with students, and they all want to find out why. The desire to find out, curiosity is intense. And we help them a little bit, here and there, so on, and what kind of mission, what experiments, and so on. And then we introduce them to what is called Cotard syndrome. Cotard syndrome is the belief that you are dead, again, because of a brain lesion. The patients are absolutely certain they're dead. This is a very strange delusion, right? So the doctor asks them, you think you're dead? Yes. Do dead people bleed? No, they don't bleed. So the doctor asked, can I do an experiment? Can I make a small incision on your finger? No, sure. I will not bleed. And the doctor makes an incision and starts bleeding. And so they look at the finger and say, oh, so dead people do bleed after all. See, the patient is actually avoiding a logical contradiction, but is unwilling to abandon the belief that they're dead. Which is extremely interesting. Okay. Now, there are a few, 2 or 3, examples of that kind. And the students really want to get more of those examples. And so, can we discuss these cases more and more? They are interested in neuropsychology. That's what happens. They're madly in love with it. So they wanted me to teach a complete course in neuropsychology. And I said, no, I can't do that. If you want to find out, you can read on your own. I refuse to go any further. But this is something that excites them. Because it is, directly, it appeals to their heart. In contrast, I use this example of continental drift. Nobody was interested. I used it 2 different years, so I finally gave up. Okay, so you have to pick examples that are the right kind, otherwise it doesn't happen. So that it's not. I understand the meaning of the question. It is difficult to gauge exactly where a student is, and then ask the appropriate question and build it up at that level, step by step. And you can even reach quantum mechanics. It's possible, but not too early. Things like calculus and quantum mechanics are so devoid of connections to actual life. Yeah. You should not teach these things at an early stage. It will be much later.
We have this basic problem of the language of knowledge that we are talking about.
Yeah.
It is mechanically unique. For example, mathematical modeling is not understood in terms of transference of thought process.
Yeah.
If this is mechanical by heart, language.
So that can be changed. That can be, you said mathematical modeling, okay? So one way of introducing to mathematical modeling would be to say, how do you measure the volume of a cow? Without actually, one way of doing that is to put cow in a tank of water and look at the displacement. If you don't want to do that, you measure something else and then calculate the volume. How are you going to do that? And the kids don't know. And you can say, assume that the cow is a sphere. This is what mathematicians do. Okay, we know that cow is not a sphere. Well, it's a reasonably good approximation. Then can you calculate the volume? Yes, of course. All that you have to do is to measure the diameter, and then you can calculate the volume. Now you say, can you improve upon it? Yes, you can say, the cow is not a sphere, the cow is a cylinder body. And there is another cylinder, there is a sphere, and there are 4 cylinders, and another tail cylinder. Pretty good, huh? And so you can calculate. That is a mathematical modeling. Of course, you know that that is not the true cow, but mathematical modeling always requires some kind of abstraction, idealization. And if you do such things again and again, they understand what mathematical modeling is. Right now, I don't think they understand what modeling is. So if they do the modeling themselves, I think they begin to understand what it means to say the cow is a sphere or the cow is a collection of cylinders and spheres. And then from that extrapolate to other kinds of modeling. So it is feasible.
It's
Yeah.
very difficult to come up with.
That, I would say difficult, yes. That would prevent me from trying and seeing how far we can go. Of course, at some point we'll say, oh, we were too ambitious, we have to cut down. That's fine, but we won't know where the limits are until we really try. And we might discover, my current hope is that given the student population, at least 80% of them are capable of creative thinking. Maybe I'm too optimistic. I may have to say not 80%, but maybe 60%. But it doesn't matter, even 60% is worth trying. So we have to try and find out where our limits are, and then after maybe 10 years of trying, we look back and say, okay, we were too ambitious, but it doesn't matter. It did create some good results. So that'll be my response to the ambitious project. Try it out, and if it doesn't reach where we want to reach, okay, but at least you've made some progress.
Two challenges.
Yeah.
One is this profoundly voluminous kind of history, enunciation of knowledge,
Mm.
enunciation, and it's very difficult to convey the entire thing to a student within this 10 plus 2 or 10 plus 2 plus 3 or 10 plus 2 plus 4
Mm.
within that period, which means you would have to omit various things.
Why not?
That's possible.
Omit all things which are not directly conducive to thinking abilities. And we have to assume that after their degree, they will continue learning. So if you leave out a few things, they should be able to learn on their own. Why not? I mean,
Just taking various aspects as history.
yeah.
For example, you follow Thomas Kuhn's paradigm. You take the latest paradigm and then train students. But they will have to revisit the previous paradigms,
Yeah.
which they need not necessarily understand.
Well, but my suggestion would be not to teach them the latest. If I were teaching physics, for example, designing a physics curriculum from school to, let's say, PhD, I would begin with Archimedes' physics, right? And then teach them how to construct that kind of physics, and we have actually learning materials in constructing a theory of motion using Archimedes type physics. And then after they have constructed that theory, you introduce them to Galileo. Okay, and it would still be, early after they have mastered Galileo in the sense by constructed Galileo's theory of motion. Then you make them construct other things, and then you come to Newton. It's possible to help school children construct Newton's theory of motion. We have tried that; it works. It's amazing how much they understand. And then you come to leave classical mechanics and go to quantum mechanics and relativity. So that should be the historical path. If you do it that way, they understand how knowledge evolves, and that's very important. And if knowledge evolves and academic knowledge corrects the preceding body of knowledge, then it goes without saying that 20 years from now, the received knowledge may not be what we believe now. So that tentativeness is part of the teaching of physics, or any subject for that, from a historical evolutionary perspective. That's important for them to get.
But do you think that the usual kind of geometry and then the trigonometric functions that they understand,
They don't understand.
at early stage, what I'm saying,
Mm.
that kind of even higher trigonometric functions they learn, these don't help understand X-ray physics.
No, so my question to you will be, why teach them those equations?
That's what I'm saying.
Skip all that stuff. In fact, instead of teaching them those equations, I think it will be much more valuable to teach them the so-called graph. You can create your own equation, and the computer program gives you a graph. Okay, to relate the algebraic equation to a visual representation using an ordinary computer program will develop their mind to the meaning of the equation. That's much more important than asking them to calculate things. So calculating, I remember looking at, when I studied trigonometry, it was such a boring stuff for me, completely meaningless. I refused to study it. I still feel the same way boring when I see the trigonometry. And the word trigonometry actually creates an emotion of hatred in my mind. But I now know that trigonometry can be taught meaningfully. So if it is taught meaningfully, then most of the existing trigonometry will disappear. Instead, it will be trigonometry thinking, a certain way of modeling, a certain way of visualizing relations.
But these visualizing devices will create barriers in the minds of several students. In the charts and graphs, all these can be misleading.
Yeah, it can be misleading. Any visual representation is misleading. But if the visual representation is combined with other forms of, for example, linguistic representation in terms of language, and finally, when the students are mature enough, algebraic representations. But you should not teach them only algebra. If your algebraic representations are combined with representation in terms of words, are combined with representation in terms of pictures, diagrams, then you get a much richer mind.
Now, imaging technology. Imaging.
Yeah. Will be used. Yeah, absolutely. Yeah. So talking about imaging technology, when I was a PhD student, I was also an intern in Bell Labs. This was in 1980, and I worked on pitch. Now there was a machine that gave me the representation of pitch in terms of a line. This was new Bell Labs invention at that time, and I worked on Malayalam intonation, and also a few other things. And I learned to hear much better by looking at the pitch tag. So if you say something like yes, yes, okay, most people would think that the pitch is just rising, the pitch is actually falling and rising. It took me some time to hear that effect. And by continuously monitoring what I was hearing and combining that with the visual information. And the learning was immense by combining the two. And what I was able to hear, what most people would not be able to hear by combining the visual representation with my hearing. So let me ask you a question, I'm pretty sure you will not hear it. There is a difference in the vowel, the final vowel, in mutta and mutta. Mutta, ni. Mutta is density. Kate, there is no word like kate. Katumaram and kate. The is different. Can you hear it? Are you sure? I couldn't hear it earlier. Oh, what about this? Talam, dalam. The second vowel, the vowel after the. Can you hear the difference between those two vowels? Yeah. So I couldn't hear the difference until I looked at the spectrographic information. And then I heard it. I combined that. I knew what was happening. So I listened to it again. And you have to have trained hearing. And the visual representations in the technology allow you to hear things and see things much better. So that is what trained perception means. So a person, a quantum mechanics specialist, can look at the bubble chamber, which is actually just a matter of scratches. But they will see an electron moving, which we will not be able to. A doctor will be able to see a fracture in an X-ray, which an ordinary person will not be able to see. You have to have both. That's the only way.
Imaging technology in this
Yeah.
And the level of assessment you need an advanced class because you need a measurement or you need assessment at some stage.
Yeah, but you don't need, for example, imagine, for example, a student in history learning physics. That student does not need the details of measurement. What that student needs are the ways of thinking like a physicist, which should be useful in history. And learning, for example, things like what I mentioned, what I learned in college, vernier calipers and broad gauge, what gauge is that, whatever gauge I forgot. I don't need, as an ordinary person, non-specialist in physics, I don't need to measure the diameter of a small wire. It's irrelevant. What I should know is the way of measuring things. Measurement is the problem. So somebody doing, let's say, for example, human studies would want to measure intelligence. They are not interested in vernier calipers. But how to construct instruments for measurement is important. So that experience is all that there is to know. So for example, what's the difference between measuring temperature using water thermometer and measuring temperature in terms of, let's say, mercury thermometer? That's important, some understanding of the problems of measurement. but they don't have to know how to measure things. So why should somebody learn, let's say, fMRI, which is measuring brain flow in neuroscience? But it'll be interesting to find out how they do it and what the relation is between brain activity and what you see in the picture. That's interesting. So we should take up those aspects and help develop the mindset of measurement as opposed to the actual implementation. They don't have to go to a lab to do any other stuff. So I don't think I have ever been to a lab or fMRI lab. I don't need that for my work. Actually, I do in linguistics. I will get my TAs to do it. I don't have the patience to do it. So that's important. I hope we haven't been having a conversation like we have been So, question for you, did we disagree? Did we engage in a debate? What did we do just now?
So, one request to me. Could you please once again suggest books? You said that people should definitely read certain books. So you could write it down. Can you suggest few books? That basic.
Oh, mathematics.
Mathematics or physics or anything which one should definitely read. Teachers and students.
Oh, I'm sorry. Yes, thank you. Yeah, I didn't have something funny. I didn't understand. Yeah. Yes.
Mathematical undecidability.
Okay, I haven't.
You know that.
But who?
You know that.
Ah, okay. It's good. Yeah. I would recommend that for the general public.
Those with less equations. Those with less equations are.
That proof is actually, without reading at least a little bit of Russell and Whitehead, or going to Poincaré, the inconsistency theorem and so on, it will be pretty difficult. Richard Feynman. Yeah. Feynman's lectures are difficult, but there are popular books like Adventures of a Curious Character. Those are not written stuff, the kind of conversations people are recording. Feynman is great. I'm trying to remember his name. Robert. Essays on the life itself. Yeah, I can.
No, there's no such.
Okay, yeah. Yeah. Robert? Yes, Rawson. Thank you. First name is Robert, right? I'm not sure about this. Rawson is right. That is an incredible book. If you can't read the whole book, at least read the first essay on what is life. I mean, he's picking up from Schrodinger's book, Schrodinger's What is Life. And I think this should be enough for at least 4 or 5 months. If you're done with these, contact me, I can recommend other things. Incidentally, there are some things that I have given here which will be of use to you. If you're interested in research, I thought I had given it here. Oh, I forgot to put it here. If you do a search for our website address is given here, and then look under courses. There are 2 courses listed. There is one of the courses is Introduction to Research. This is a course that we taught about 3-4 years ago to the research across domains. And this is how it happened. I was teaching this course for students in ISER Pune, and because of COVID, I couldn't teach it in the regular classroom. So we decided to do that online. And so some of my students said, why can't the other ISER students also join? So I said, yeah, why not? If it is online, the physical presence doesn't matter. So we invited the ISER students, other ISER students. So they said, look, if all ISER students are coming, why not IIT students? So we opened it to all IIT students. Then they said, why not the other students? So it's okay, just write to anybody that you're interested in. So there were people from Central University, Delhi University, there was something like 1,500 students online. Of course, what happened was many of the people who signed, it was a free course, right? So everybody joined. And they discovered that in order to continue, they had to do some work. So gradually the number dropped. But we still have something like staunch supporters who keep raising questions and discussing questions even after 3-4 years at the website for the course. It's still called Introduction to Research. There's something like 100 and odd students from, I have no idea where they are from different parts of India, some from abroad, who are discussing various issues. Yeah. So do look at it, look at that Introduction to Research, not just the first year foundation course. Where the first year foundation course can go to the details, the later stage.
Have you heard of Noam Chomsky? He worked with.
Oh, okay. So wait a minute. Well, I don't understand this. I mean, I worked with Noam Chomsky. Suddenly there is a difference in. why is Chomsky important? What has Chomsky done? Was he a great poet or a painter? What? Why is Chomsky important?
BA students language acquisition device. Language acquisition device, all those things they learn in their BA courses.
Oh, okay. I don't think it's a good idea to teach Chomsky as part of a BA program, because Chomsky has systematically said, if you're interested in language education, do not come to me. The kind of theory that I'm pursuing is useless for language education. And he's right. He systematically said, don't use this, because the kind of stuff that Chomsky is interested in is what you don't need to teach. Children would pick up without teaching. And what you need to teach, things like agreement and the kind of spelling and so on, Chomsky has no interest in that. So the past tense go is went. That has to be taught. And Chomsky said that's boring stuff. So the concerns are different. I mean, Chomsky has explicitly said, if you're interested in language teaching, go to Renan Martin traditional grammar. It is much more useful than what I do. And I think it is not a good idea to try and lecture on Chomsky to the suffering BF students. I don't think you will understand a syllable of what Chomsky is saying. But his work on political theory would be of interest. He's an anarchist. It's much more interesting. He's a radical leftist political theorist. In addition to being the person who started the something in computer science and also in linguistics. And by the way, Chomsky was the person who made me aware of the need to show that your teachers can be wrong. That was the first thing that I learned at MIT from my teachers, saying, you didn't come to MIT to accept whatever we are saying. Your job as a graduate student is to show us that we are wrong and why we are wrong and improve upon us. That was the first instruction that I learned in my first semester. And I think that was extremely valuable learning for me. This is what I'm trying to kind of suggest to you, that your job as students is to show that your teachers are wrong. That's a direct Chomskyan application.
Learning is not to repeat, not purpose said,
Yeah.
not to repeat what is already known, but to reject.
Yeah. Yeah. What are the that's the meaning? Yeah, that's actually the yeah. I don't know if they often finding, but they were approaching language. They're both valuable. Yeah.
So for a formal vote of thanks, I invite Tichu, research officer.
Professors, dear friends and colleagues from SNG, GK, Pothencourt and KSGC, well, that was really an engaging session. Actually, we unlearned rather than learned, I think. That was really engaging and very enriching. I'm sure that it will inspire the future teachers and all of us. So let me take this opportunity to formally thank our source person, Dr. K.P. Mohanan, and also Professor Rajan Gurukal, the Vice Chairman of KSGC, Member Secretary Dr. Rajan Varghese, and all the teachers and students from Pothencourt B.Ed College. We sincerely thank all of you for your valuable time and for your, that you came here, you were here. I hope that you could understand much of the things that are said here. We wish you all the best. I also thank my colleagues. Once again, thank you.